Okay, thank you, Sir Hanke. And our next speaker is Mireille Schnitzer from University of Montreal, where she is an associate professor of biostatistics. So today she'll be talking about outcome adaptive lasso for confounder selection with time variant treatment. So take it over, Mireille.
Great. Thank you so much, Linbo. Can you see my, actually, they're not full screen. Thank you so much, Limbo, and thanks to the organizers of this conference. It's really my pleasure to be here. I'm going to talk today about some early work on this topic, but I'm excited to share. I think it's super interesting. So I'll be talking about an extension of outcome adaptive lasso for the situation where you have time-varying treatments, and so you have time-varying confounders that can be affected by previous treatment. This is joint work with Ashkan Ertfai, Denis Telbo, and Guambo Wang. So the context that I'm in is really standard marginal structural model context with conditional exchangeability. So I'll go through this this carefully. So we have a data structure where we have measured covariates and binary treatments at different time points, and this is assumed to be the time ordering. And at the end of this time period, we have a measured outcome, which we're going to say is continuous. We define the counterfactual outcome y a bar as the potential outcome under a fixed treatment pattern, where each of these fixed treatments or exposures is either 0 or 1. And then we define a marginal structural model, and an example of a marginal structural model that smooths over the effects of treatments is written here. It's a model of the expectation of the counterfactual outcome, which can be conditional on one or more baseline covariates. So here we just wrote one baseline covariate, and cumulative A bar means that we count the number of ones in the exposure pattern, and we look at the association between that and the counterfactual outcome. The true parameter values of the marginal structural model minimize the risk under squared error loss function, where the outcome is the counterfactual outcome. And so that's these parameters are our target. So we assume consistency and absence of interference, and also that we have measured a sufficient adjustment set, or some people call it an adjustment set, to satisfy the conditional exchangeability assumption. Here it's sequential conditional exchangeability in the longitudinal setting. And so we assume that we've measured covariates LT bar that satisfy the independence between the counterfactual outcome and treatment at each time point conditional on a sequence of past treatments. We may have measured more covariates than necessary, but we assume that we have a set that includes a sufficient confounder set and that the larger set is also sufficient to adjust for confounding. We also have to assume positivity, which means that at every time point, given any covariate history and any treatment history that is possible, that is supported, we have a probability that is non-zero of having either exposure. And then with these assumptions, we have identifiability of the expectation of the counterfactual outcome through this nested G form. You may call it a nested G formula here, which is present in Jamie Robbins' original papers. So it might be evident at this point that there is a lot of sparsity when you do longitudinal causal inference. This is, of course, very, very well known. And it really comes up as a challenge in a typical epidemiological application almost 100% of the time when I think, oh, this is a straightforward application of any longitudinal causal method. We have sparsity problems, and then we have to do something either ad hoc or go into sort of more technical applications of methods or change the target of inference. So the sparsity arises because we need study and outcome information for any history of treatment and baseline and time updated covariate values. Okay, so you need a lot of data to sort of support everything that you need to estimate. And so this is unlikely with many time points where treatment or exposure may change. Okay, so it also sort of depends on how you define your problem. Often it works out really well if you have treatments that are monotone, so people switch at some point and then they're considered to stay on their new treatment. But if you're considering exposure that can go on and off, this is where sparsity really becomes a big problem. And so there are different things that you can do. That you can define a stochastic intervention, so you can really change the scientific question of interest, which is a really interesting approach that we're using in one project. And there are other situations where you might want to smooth over the models. And so this is typically not data driven. These approaches might include defining a smooth marginal structural model, as I did just a few slides earlier, instead of looking at the effect of every exposure. You might also pool models over time points. So the models that we need to estimate the parameters of interest include the propensity scores at every time point. These are the models, models for the probability of treatment. And also you need to model the conditional expectation of the outcome if you're using well, if you're using a regression method, or if you're using a doubly robust method like AIPTW or target maximum likelihood estimation. So you can pool these kinds of models over time points, with basically smooths over time points, and makes a lot of assumptions. And this is typically done in a non-data driven way, at least in my experience, and when we're talking about sort of the practice of causal inference. And so this is what I wanted to address. So in this talk, I'm only going to be focusing really on IPTW as the causal estimator. And so we're going to be focused on estimating or modeling the probabilities of treatment that we're going to use in the weights for inverse probability of treatment weighting. So this method involves estimating these probabilities of treatment at each time point. They're conditional on the history of covariates, and also setting the past treatment to a given pattern. And we do this for every time. We have to estimate these probabilities, model and estimate these probabilities at every time point. And so once we have that, we regress, or one way to implement IPTW is to regress Y on the covariates in the marginal structural model, using weights equal to these estimates here, where you can stabilize. That's an option, a very important option. Here I'm defining the stabilized weights conditional on the covariate in the marginal structural model only. There should actually be a 1 here, and only the most recent treatment. Okay, I'm doing that on purpose, and there's a reason why later on in the talk you'll see. So that's a partially stabilized weight. And we also need to talk about estimation by outcome regression, even though that's not specifically used in the IPTW, but it's used in the method that I'll be explaining. So we can recursively define these nested expectations of the outcome. So at the first, well, actually, it's at the last time point. For t is equal to k, we define q bar k as the expectation of y, conditional on the history and setting the past exposures to some pattern. And then we take that and we nest it into another expectation, and we define that as q bar k minus 1. That would be conditional on the history up to k minus 1, and we do that recursively. So we've defined all of these q bar t's, and for brevity, I will write those in this way. And there, notably, you have to adjust, you have to condition on a specific covariate pattern. So that's and that's written above here. And then define q bar s to be the stacked vector of all of those vectors for every possible pattern of a bar. And so under the causal assumptions, the marginal structural model parameters minimizes the least squares risk function of the model with q bar s not as the outcome. Okay, so this represents an outcome regression way of estimating the marginal structural model parameters. So very often in practice, analysts will follow recommendations or just sort of examples of practice that are present, for example, in the very famous paper by Robinson and Brumbach, and also their companion papers, where they're going to pool the treatment models over time points. And so this can often help in sparse settings. So here's an example. So you fit a pooled model where each treatment is regressed on the past 2 time points of treatment and the current updated covariates, baseline covariates. Perhaps these are non-time varying covariates, and then some function of time. So the modeler has to decide, the analyst has to decide how far the look back period goes for every treatment model, and if we're going to consider like previous covariates, and also one has to consider the correlations between the variables, since they're measured. The same variables are measured at different time points. So all of this really matters. A lot of subject matter knowledge can be used here. But with sufficient information, and I think this was subsequently recommended, one might model the probability of treatment stratified by time point. So each time point gets its own model. But you still have to make decisions about exactly how far back you look, even when you do it in this way, and exactly which variables you're going to include at every time point. And so here I wrote this ST bar as sort of a selector of which covariates are included in the model. So there's a lot of literature on statistical confounder selection and information and sort of advice on what to include in these propensity score models in both single time point settings and multiple time point settings. So some early work made it clear that adjusting for things like instruments, so instruments can be helpful for estimation, but they can hinder estimation in this context where we're trying to adjust for confounders. For example, Burkhardt and Schneeweiss et al. In 2006 demonstrated that we want to adjust for confounders, but if we adjust also for pure causes of the outcome, then we can, reduce the estimation variance. And then there were several other papers that talked about how overadjustment can inflate variance. So overadjustment here would be adjusting for the variables that don't actually remove confounding bias and aren't correlated with the outcome. And there are many statistical approaches. Basically, these are in the single time point setting as far as I know. That's basically what I've seen. So there's in particular collaborative targeted maximum likelihood estimation can be presented as a variable selection approach, or it can be presented as sort of a more general, possibly non-parametric approach to estimating the propensity scores. There's the outcome adaptive lasso by short range Stratified, which is what we want to extend. There's also a version of that uses elastic net that can better account for correlated covariates. There are a lot of Bayesian approaches. Sometimes the Bayesian perspective is more natural for variable selection. There's also large literatures on causal discovery algorithms and theory for deseparation identifiability and fully or partially known causal graphs that do relate to variable selection. There's also direct machine learning approaches in the semi-parametric model. So for example, cross-valid target maximum likelihood estimation and sort of another version where you have the doubly robust non-parametric inference and the very related double or debiased machine learning approach. And then in the time varying setting, which is what I'm interested, there's less to my knowledge. So one early paper that gave empirical results for how to select variables and in doing so potentially misspecify your treatment model with the goal of improving estimation of your target parameters. There is this paper by Lefebvre, Delaney, and Platt. We developed longitudinal CTMLE, we published this in Biometrics not that long ago. And then Rodnitsky and Schmuckler in 2020 gave general analytical results for asymptotic variance inflation in the semi-parametric model, which is a very, very interesting read and related, very much related to this work. So to formalize a bit, we're going to define our selection objectives through a simpler setting with just 2 time points. So we have A0, A1, 2 binary treatments, and then we have 2 covariate sets. So this can be multivariate L0, L1. We want to potentially, so our goals are to potentially reduce the vector covariate sets while maintaining control for confounding with the goal of reducing estimation variance in the parameter of interest. And we also want to selectively collapse time-specific parameters in the treatment models to allow for data adaptive smoothing rather than doing the smoothing sort of in a non-data adaptive way, which can lead to bias. So the key thing is to see that we can write, it's pretty straightforward, but we can write the pooled treatment model, the model for the treatment at any time point conditional on the past. Here we're looking at the 2 time point setting, so it's a little bit easier to see. We can write it actually in a way that's an equivalent restriction to the stratified treatment models. So here we have indicators for time point 0. So we have 2 parameters for basically the probability of treatment at time 0, the intercept, and then the coefficient of L0. And then we have indicators here for the later time points. And so this would be the intercept for time 1 And then here's the coefficient of L0 at time 1. And then this is a covariate that only happens at the later time point. And then we adjust for A0 at the later time point. And so there are coefficients for that as well. So we have this vector of alphas. And so this is what we need to estimate. These are the parameters we need to estimate in order to estimate our propensity scores. And so we define M here as the corresponding model for the probability of treatments at time t is equal to 0 and 1. And so we're going to work in this model to do our variable selection and our potential collapsing of the coefficients. So we also need to consider the working structural outcome models in order to define how we're going to be doing our variable selection. And so here we consider, should be expectations, but here we consider the two structural outcome models as the expectations of the counterfactual y's, conditional on all of the covariates up to each individual time point. And at the second time point, we also put A0 into the model because that's in its history. And so we basically need to estimate these betas. We're going to define a beta dagger to be the corresponding indicator vector of the non-zero elements of beta. And we'll always be fixing the intercept and treatment terms as non-zero. Okay, and we're going to use these betas to do our variable selection in the propensity score models. Okay, so this is our variable selection objective. It's to select variables into the treatment model at time t that have non-zero coefficients beta and the structural model for the outcome under intervention up to time t. So specifically, we want to estimate the coefficients of the propensity score, where we basically remove or set to 0 the alpha parameters where the corresponding beta is 0. Okay, so that the beta dagger is telling us which ones are 0, which ones are not 0. Okay, so in order to do this, we have to estimate these Q bars, and we do so by regressing for time point 1. We do so by regressing y on the history, and then we generate predictions from this model by imputing the treatment to values A0 and A1. Then we run a pooled regression of the stacked vector. So we create the stacked vector using every combination of the treatment values here. We run the pooled regression on the covariates L0, L1, and A0, and this gives us estimates of the structural model 5, where so we got the beta estimates 2 to 5. And then we do something similar for the next time point, except so we have Q bar 1, and so we regress this on L0 and A0 using a flexible form. Ideally, we use this model fit to make prediction setting A0 equals to a value to obtain estimates Q bar 0, and then we run a pooled regression of the corresponding stacked vector on the covariate 0, and this gives us estimates of the parameters of the structural model 4. Okay, and this gives us the entire vector of beta hats. Okay. And so using those beta hats, we're basically going to run a pooled outcome adaptive lasso. So those beta hats make their way into the adaptive weights, which are now outcome adaptive weights. Okay, so those omega j's are going to be defined as 1 over the absolute value of the beta hat j to the power of gamma. So gamma is one of the tuning parameters. And so this is how we basically penalize our logistic regression function. And so we can use the results in short read and Urtify to say that this estimator is asymptotically normal and consistent for the selection of covariates in the model, consistent for the target variables, the ones that have betas that are not 0. But it requires conditions on the convergence of the regularization parameter lambda n, and also of the estimates beta hat j. And so this is where there's a big difference between a longitudinal version of this method and the single time point. The longitudinal version relies on estimates of these Q bars that are nested. And so this seems straightforward, but that's the challenging part. It's a bit of a catch-22. You have to estimate the Q bars in order to get to do the variable selection and the propensity score. So here's a rationale of the qualitative target for variable selection. So the procedure is basically removing extraneous variables from our covariate set that are simultaneously found to be independent of YA bar, given the remainder of the adjustment set and past treatment. So we're basically just removing the extraneous variables that aren't correlated with the counterfactual outcome. At time point 1, this corresponds exactly with the single time point outcome adaptive lasso objective. Okay, but we wrote it a little bit differently, but it corresponds. At the other time point, it's a little bit different. So here we just have that we assume that there's the conditional exchangeability between counterfactual outcome and A1, and then we find that that there are some variables in LT bar that are independent of the counterfactual outcome. And then what we're left with is we retain our conditional exchangeability with the remaining covariates. So here we're also adjusting for the remaining covariates they see in the model. And we're doing this directly by estimating the beta parameters. This is all done under the linear model, of course. So we call that a working linear model. And so at time point t is equal to 0 works out similarly. We assume that we have conditional exchangeability, and then we are basically removing the components of L0 that are found to be independent of the counterfactual outcome conditional on the other elements of L0. And here at t is equal to 0, we evaluate this independence not using the outcome, but using the estimates from the first stage. Okay, the Q bar 0 stacked. Okay, then so we've defined the objective function. In order to operationalize this, we have to tune. It's very, very important to select our tuning parameters. And so we had to determine what kind of balance criterion we were going to be using. And so this was tricky. We are extending the what was proposed for the outcome adaptive lasso, which basically involves at the single time point, you just have like one treatment. So we're looking at the difference between each covariate between the treated and untreated groups, multiplied by the absolute value of the coefficient in the outcome model. So for us, that would be the betas. So here we're standardizing the betas with standard error. And we have to look at this comparison at each time point for each covariate. So I started with diagnostics for longitudinal balance in a paper by Jackson. The challenge there is that if you stratify by the full treatment history, which is what is proposed in that paper, you end up with very small strata. And so we wanted to avoid conditioning on the full on the covariate and treatment history. So here we're using this is the reason why we didn't fully stabilize the weights. We would expect a balance with these partially stabilized weights at each time point without conditioning on the specific strata beyond just the treatment at that time point. So that's the variable selection stage. I'm finding that just kind of the mechanics of the problem, it's necessary to split these two stages, so we're still at the exploratory stage where we're trying to see how this works. So right now I have a second stage for model pooling. So the goal here, so I'll describe the goal and then I'll explain the challenge a little bit. So after variable selection, we've selected the subsets here. I'm calling them L bar dagger. And then we will fit a model just with a subset of covariates. So in this model, if we have that alpha 1 dagger, which is the coefficient for L0 at time 0, and alpha 3 dagger, which are the coefficients for L0 dagger at time 1. So if any components of those two coefficients are very close and it's beneficial, then we want to fuse those two coefficients. And so you can see that we're going to be using the fused lasso here, which is what really corresponds to our goal. Okay. And the reason why this is challenging is that those coefficients will vary depending on what covariates you're actually including in this model. So which is why if you have the target really has to be after variable selection, because it's not the same thing to do this before variable selection. Okay. So this is the objective function. So we basically use a modified version of the adaptive fused lasso, where we have this fusing component where we want to shrink on the difference of the alpha 3s and alpha 3, alpha 1, which are the two corresponding. I wrote this saying like, okay, like simplifying it, making it one-dimensional, but you just have like a summation over all of the different components. And then the adaptive weights are the first stage estimates from the outcome adaptive lasso. Okay, so we've already done the variable selection. We removed the variables that we don't want, and we have estimates of these alphas. And so this is the adaptive weight that we're using. Okay, and here the goal is different. We're not assessing balance anymore. We're really just trying to get in this reduced model. We want a good fit. So previously the adaptive fused lasso evaluated selected tuning parameters using BIC. So we do that as well. So the adaptive fused lasso has oracle properties. We don't really want to select the true value variables that go into the propensity score model because those are the predictors of treatment and we want to avoid instruments. So I have 5 minutes. I see Limbo. Should I continue?
Yes.
Yeah, okay. So I have some preliminary simulation study results. We have 2 scenarios with the same DAG and the same propensity score models. So it's a 2 time point problem. We have instruments I0, I1, so we want to select those out. So one thing that's interesting is I1 is caused by L0, so it's correlated with the confounder at the first time point. L0 and L1 are true confounders. We want to keep them in. These are all univariate. So the variable selection should select L0 into the A0 model and L0 and L1 into the A1 model, and a sparse procedure. So I cooked this so that a sparse procedure should fuse the coefficients of L0 if conditioning on only L0 and L1, but if you condition on the instruments as well, those coefficients will be quite different. So this is what we get. So here we have a mean squared error comparing the G computation, are these little triangles, the full IPTW squares, the oracle IPTW with fusion is the cross, outcome adaptive lasso is the box, and fused outcome adaptive lasso, which has the 2 steps, is the circle. And so we see that G computation main term, so it's correctly specified here. So it's just sort of a benchmark. This is like efficiency bound, whatever. So this does the best. And then our methods work as well as the oracle. The fusion doesn't really give you any gain in the mean squared error. It's probably because it only produces 1 degree of freedom. And then everything is better than the full IPTW model that doesn't have any variable selection. You see that the bias for G computation is the best and everything kind of bounces around. Here is the cross. So that's for the oracle model. And our methods are over here. IPTW with all the variables does worse at first and a little bit better later on. In a second scenario, we added effect modification, like in a nonlinear way, squared covariate in the outcome model. So this completely messes up G computation. It has the highest mean squared error and bias. And because we're using the same functions to estimate those Q bars, I wanted to see if the method was still robust. And we see that in this simulation, it indeed was. These methods performed very well as or just about as well as the oracle. I'll quickly go through this. So looking at the covariate selection and fusion results, the results really depended on the gamma parameter for the outcome adaptive lasso. So if we do a more aggressive selection with a larger value of gamma, we get better, we select out the instruments much faster than if we have a lower value of gamma. So this was really interesting. Now, when we used the balance criterion, we actually ended up selecting the lower value of gamma almost all the time. So that was a bit weird. And so we're learning a lot of stuff as we do this. The fused outcome adaptive lasso, where we have the oracle at the first step, selected perfectly. So that's good. That's just to show that it does what it's supposed to do. And then if we run fused outcome adaptive lasso, just always selecting the tuning parameters, it does pretty well. Doesn't do so well to select out instruments. And so we see that this converges for gamma is equal to 2 very well. But what we don't see is that for gamma equal to 1.1, it converging very quickly at all. And we don't see the fusion converging here. So that's another interesting thing, which makes sense. We have many steps of estimation. Everything we're assuming converges appropriately. For the second scenario, We have the true betas are in the bottom here in pink, by the way. So really we want to keep the same variables in the model, but because of the misspecification, it messes up one of the outcome adaptive lassos, and which doesn't select out the, which doesn't select in a true confounder. So that messes up one of the outcome adaptive lasso. And so there's a lot more stuff to do. We have to work in higher dimensions to evaluate whether this is beneficial, and we have to work over more time points, see if the fusion can be beneficial. And I just want to say, why am I working in a regularization approach? There are also non-parametric approaches that we could consider. This potentially could be extended to a non-parametric approach using highly adaptive lasso. I think for a first step, well, it's transparent and intuitive, and some investigators, applied investigators, sort of like this idea. It also is teaching me more about the mechanics of longitudinal variable selection because it's subtle. There are a lot of limitations. Currently, we cannot select model features. We're relying on misspecification of the treatment models, which is naturally because of non-collapsibility and also just because they're parametric models. This can be fooled by M-bias structures in the variable history. And of course, we require the estimation of these Q bars, but that's similar to longitudinal CTMLE. So this is a problem we saw there as well. And that's it. Thank you very much. Thank you so much, Limbo and organizers.
Okay, thank you so much, Maria, for a very nice talk.